My name is Dean Goodman. I'm going to be demonstrating SurvNET today. When you first run SurvNET, which is Carlson's network least squares adjustment program, you will see the startup dialog, which allows you to create a new project or open an existing project. I'm going to create a project and go from beginning to end, but before I do, I want to talk a little bit about the advantages of network least squares over traditional data processing softwares like Compass Rule, Transit, and Crandall's. First of all, it allows you to be very creative in your field data collection. The order of the data does not matter. You can have data that begins at one point and goes to halfway through the project, and then the next day starts at that same point and goes the other direction through the project. Control points can be anywhere in the traverse. This is an extremely powerful feature of SurvNET. Control points are coordinate points that basically constrain the adjustment. They're known points that you do not want to change. Control can also be azimuths. For example, solar observations or Polaris observations or azimuth marks can be used as control. SurvNET allows you complete control over the adjustment process, allowing you to weight measurements and control points. SurvNET handles procedures like triangulation, where you have angle-only records, and trilateration, which is distance only, and of course resection, where you're locating known points from an unknown point. SurvNET handles redundancy, where you locate a point from several different locations. For example, if you are traversing and turning an angle to a radio tower from several different traverse points, it can process that type of situation. One of the big advantages today of using a program like this is that when you're in a state plane coordinate system, SurvNET automatically adjusts your ground distances to grid distances. Since your GPS control points will be in state plane, this gives you much better closures when going from one GPS control point to another. And this is done all automatically. The SurvNET allows you to process GPS vector data and traverse data and levels all simultaneously. SurvNET will allow you to see your traditional linear and angular closure reports. SurvNET has advanced blunder detection tools to allow you to track down problems in your traverses. It has very extensive statistical reports, which will give you much more information about your traverse than the traditional error of closure reports. We also designed ALTA certification reports inside of SurvNET, so you can certify as to ALTA standards. I'm going to create a brand new project. I'm going to call this project Carlson. When you create a new project, you will have to answer some questions about the project settings. This dialog is the main dialog in SurvNET. It has several tabs for different types of options. The first tab is your coordinate system. The coordinate system I'm using in this project is NAT 83 state plane coordinates, and I'm in Georgia West Zone. We also have the option of you selecting a local coordinate system, NAT 27, UTM, or you can select user defined and define your own coordinate system. This is useful if you're in a system that we don't support. Basically, you can give your system a name. You can select the ellipsoids that you want to use. We have several ellipsoids that are already here, or if none of these are the ellipsoid you want to use, you can select user defined. And then you'll select your projection system. These are the projection systems we support, and your datum parameters. I'm going to select NAT 83 and Georgia West Zone. We have two different adjustment models. We have what we call the 2D 1D model, and we have the 3D model. The 2D 1D model will pre-process your data and adjust and reduce slope measurements to horizontal and vertical components. It's the horizontal and vertical components that will be adjusted. The 3D model will directly adjust slope distances and zenith angles. The advantage of the 2D 1D model is that it can handle both 2D and 3D control in the same project. Both Carlson, SurvCE, and CG Field data collectors allow you to collect both 2D and 3D 2D and 3D data in the same files. If you want to process GPS vectors with your traverse data, you'll have to select the 3D model, in which case all data has to be 3D data. The particular project I'm about to process, I'm going to use the 2D 1D model. Geoid modeling, this is used to calculate the vertical scale factor. In this particular case, I'm just going to use a zero separation. It makes very little difference on the scale factor calculations. In order to calculate the elevation scale factor, you can either give it a project elevation. If you're working on a completely 2D project, you can enter a project elevation to be used. In my case, I have a 3D project, so I can actually compute the scale factors directly from the elevations in the raw data file. My elevation units are US feet. My horizontal units are US feet. The next tab allows me to select the files for processing, the input files. I'm going to select a raw data file. This is a CGR file. That is a CNG raw data file that was given to us by one of our clients. Of course, you can also select Carlson RW5 files. We process either of them or both of them very well. The next field, which is grayed out because I did not have 3D models selected, is for selecting your GPS vector files, and we support a half a dozen of typical file formats. The third box allows you to select your level files. We support both differential level and trig level files. Both of these files can be collected from SurvCE. The last box is for supplemental control files. If you have a coordinate file that has your control points in it, you can select it here. We support, of course, CNG and Carlson coordinate files, as well as Autoland desktop, simplicity, and straight ASCII file formats. I prefer to keep my control inside my raw data file, so I am not going to select a supplemental control file. The third tab is pre-processing. This is what we do before we actually run the network least squares adjustment routines. The first checkbox asks whether you wish to apply curvature and refraction corrections, and this field here, point substitution string, is a very useful feature if you have a data collector that will not let you call points what they actually are. For example, if you have a data collector, if you're locating a point that already exists, say you're locating point 5 and you've already located it from somewhere else, or it's already part of your raw data, they will not let you call it point number 5, so you say call it point 100. This allows you to put in the description of that point 100 what the point really is. For example, you could use the equal sign as your point substitution string. If we find equal, we will look for the number after it, and so when you located point number 100, you could say equal 5. In that case, we will treat that line of data, or that point 100, as if it were really point number 5. Point number 100 will never be used or will never exist. It's very important that you call points what they really are. Part of the power of the network least squares is to be able to handle redundant information, redundant data. You don't want 5 coordinate points located on top of each other just because you checked into that point several times. But you want all that data used when it's calculating the values of that coordinate point. The next field allows you to set up a closure file. Since, as I said before, the data can be in any order, we need the client to be able to tell us what the traverse setup is. So, for example, I'm going to open an existing traverse closure file that I've set up for this project. And I have 2 traverses that I want to see closures on. The first traverse is a point-to-point traverse. It begins on 2 points and it ends on 2 points. I have vertical closures on and angular closures on. The second traverse is a loop traverse, which begins and ends on the same point. Again, I have vertical and angular closures turned on. As you can see, this goes from all the points from 103 to 113, then to 144, then to 128, then to 124, etc. until it closes. This defines the traverses, and this gives us the information we need to get the closures. The next part of the pre-processing dialog are where you set up your acceptable tolerances. When you're turning sets of angles and distances to points, we'll average all those angles and distances to a single angle and distance for processing. When we do this, we'll keep track of the high and low values of the angles and distances, and if they fall outside of your tolerance settings, we'll warn you inside the report. The actual angles and distances will be reweighted based on the number of times you measure to them. So even though we may take 4 angles and average it down to a single angle, the weight assigned to that angle will be more than if you did turn just a single angle. The next tab is for where you set your standard errors for your projects. This is the way you actually weight the values or weight the measurements. There's basically 4 different types of standard errors. There's your measurement standard errors, and these will generally be taken directly from your instrument specs. For distances, I have it set to 1/100th of a foot plus 5 parts per million. For your angle standard errors, I have it set to a pointing of 5 seconds and a reading of 10 seconds for both horizontal and vertical. The reason why we set up 2 different values for horizontal and 2 different values for vertical is basically a way to allow you to perhaps take into account the measurement conditions. For example, say I have a 10-second theodolite that I measured angles with, but it's a very, very hot summer day and it has heat waves. I can say, well, my pointing error might be 20 seconds. And if it's a very cold, crisp winter day, I might say my pointing error might be 5 seconds. Since these are basically instrument-specific errors, we allow you to save your standard errors into a file. For example, I can say I want to load my Leica 1200 standard errors and hit open. This basically read standard errors into all these fields that I had previously set up in a file. If I want to save whatever I have just created, I can do save as, give it an instrument name like TopCon 300 and hit save. The second box allows you to set up the instrument setup standard errors. How close can I set up my target over the point? How close can I set up my instrument over the point? How close can I measure up to my target? How close can I measure up to my instrument? The third box allows you to set up control standard errors. Now these will be project standard errors. If there is no standard errors assigned directly to control, these project standard errors will take precedence. Azimuth standard error I have set to 5 seconds. Coordinate standard errors, north, east, and elevation. This box is for differential level errors, and the final box is for GPS standard errors. Since I don't have either of those types of files in this project, I'm going to skip those. The next tab is for the adjustments. The network least squares program adjusts on an iterative process. It will apply a certain amount of correction based on the weights to each measurement and then calculate coordinates for everything. It'll compare those coordinates to the previously calculated coordinates, and when they don't change anymore, it considers itself complete. You tell it how many iterations you will allow before you give up, and you tell it your convergence threshold. When coordinates do not change more than, I have it set to 2/1000ths of a foot, it will consider the project has converged. From practical experience, we found that most projects will converge after 3 to 4 iterations, so 10 is very reasonable. If it goes past that, you probably will never converge. The next fields in the adjustment tab are for your statistical reports. You state what confidence interval you wish to see. For example, the Alta standards request a 95% confidence interval on their positional tolerances. This box is for calculating relative error ellipses, which is another term for positional tolerances. We have a checkbox which will enable side shots for relative error ellipses. If you don't have this checked, side shots are just set aside. All the traverse data is processed, and then the side shots will be calculated off of the adjusted traverse points. This will save time if you have a lot of side shots. But if you need those side shots for statistical reports, you'll have to include those in the adjustment process. This next field allows you to select what we call a relative error points file. Since relative error ellipses are basically determined by 2 points, you will have to tell us which points you want to check between. If you have thousands of points in the file and you want to check every possible combination, it can take a lot of time. So we allow you to create a relative error ellipse point file, and I have one created. It has basically 2 separate boxes, one that says check all connections and one that checks specific connections. So in this case, I have points 100-200, that's 100 to 200. I want to check every possible combination. That's like from 100 to 101, from 100 to 102, from 100 to 103, etc. You can select points by point number, or you can select them by description. For example, I could say I want to select all points with a TRAV description. This box here allows me to tell how many connections I wish to display, since there are literally thousands of connections possible. I decided I just want to see the worst 20. Specific connections, I've selected that I want to check specifically from 102 to 110 and from 118 to 105. Those are 2 connections that I want to see for sure. This last checkbox is whether you want to include an Alta tolerance report. and the tolerances for that report. Currently, the ALTA standards are 7/100ths of a foot plus 50 parts per million. The last tab allows you to select your output options. How many places after the decimal you want to see in printouts for your north, east, your elevation, your distances, and your directions, which are bearings or azimuths. This is a format dialog. Do I want to see my directions in bearing format or azimuth format? Am I using degrees or grads? How do I want my reports printed out? Northeast, east-north, XY, YX. What value shall I assign to no elevation? This particular value you see here is C&G's no elevation value. Carlson currently uses 0 as a no elevation. Many other software packages have different values for no elevation. Coordinate file output. When it calculates coordinates, if you want to output to a file, you check the right to coordinates. You select the file you want to output to. We again support all the C&G Carlson formats. We always will output to an ASCII output file, and you select here what format you would like that ASCII file to be shown in, and the northeast and elevation precisions shown in that file. I'm going to turn off the right coordinate point file current for now until we get it processed and I'm happy with the results. So now I've set up all the settings for my project. I can go in and take a look at the project. This little eyeball gives you a graphic view, and as you can see, we have a very good network of traverses. All the green lines and triangles are traverse points. The blue lines and circles are side shots, and the red points are my control. As you can see, I only have 2 control points in the file, and they aren't contiguous. They're completely separate from each other. One's at the beginning of this traverse, and the other one is somewhere on the other end. Very few software products can process and calculate coordinates unless they start on a known point with a known azimuth or start on 2 known points. We put a lot of effort into SurvNET to allow it to be smart enough to calculate coordinates with just 2 control points that don't necessarily have to be next to each other. You can have as many control points as you want. I could have control points all through my traverses. It would adjust all the data to those control points. Before we process this file, I want to go in and take a look at the raw data. This will take me directly to the raw data editor. Since it's a C&G raw data file, it would automatically run the C&G editor. If it was a Carlson raw data file, it would automatically run the Carlson raw data editor. As you can see, this file consists completely of raw data, instrument setup, and 4 side shots. You can see that they've turned sets to each one of their traverse points. At the very beginning of the traverse, we see that we have 2 control points. These are coordinate records, point number 43 and point number 104. This record prior to the coordinates is a standard error coordinate record, and it has an exclamation point in the north field, in the east field, and in the elevation field, which we take to mean hold these points fixed. This standard error coordinate record has asterisks in the fields, which means go back to project standard errors. So the fixed coordinate points will only apply to these 2 coordinate records. I'm going to go ahead and show you a quick way to enter these types of values. First, I'll go ahead and delete my control. I'm going to go up to Insert, and I'm going to insert coordinates from File. I'm going to select a coordinate file. And I'm going to say I want to select by description, and I'm going to select all coordinates with a CTRL description and say add from file, and then I hit OK. That quickly gets my 2 coordinate points in the raw data file. I'm going to insert a standard error record, and I'm going to say I'm going to hold them fixed, so I'm going to enter an exclamation point. You can see that you can enter standard errors for not only your control, but also your measurements, distances and angles, or your instrument setups. So if there's anything, if there's for some reason you wish to assign specific weights to certain measurements, you can enter those directly into the raw data file. You don't have to fill in anything that you're not going to actually use. So it's inserted a standard error record. Now I'm going to go and I'm going to insert another one at the end here. And I'm going to say set back to project defaults, which puts asterisks in all the fields, and hit OK. And I have my control in my raw data file. You can also view your traverses inside of your raw data editor. So we have a raw data file and everything looks good. I'm going to head and close it. I'm going to save my changes, and I'm back into SurvNet. The next thing I'm going to do is I'm going to process the file. So I'll hit Process, Adjust Network. And as you can see, it creates a report file. It also creates an output file, which is just an ASCII coordinate file, and it creates an error file. The error file contains basic warnings, errors, and closure information. Let's go ahead and go through the report file and discuss it. Basically, this tab here gives you the entire report, and the following next tabs will give you pieces of the entire report. It makes it a lot easier for you to go directly to the part of the report that you want to see. For example, first thing I'm going to look at is my pre-processing. This gives you basic information about the project. It's, state claim coordinate systems, units, confidence interval, all the settings that we set up for this project. Then it gives you your tolerances. As you can see, we have some vertical tolerance errors, vertical distance errors that exceeded our tolerance. This vertical distance from 104 to 103 has a 5/100ths difference when we were pre-processing the data. We have some horizontal distance error tolerances. I don't see any horizontal angle tolerances. But the first thing I generally do is scan down through the tolerances and see if there's anything that really strikes me as being a blunder or something incorrect. The next tab shows your unadjusted observations. These are my control points, 43 and 104, and as you can see, they're held fixed. These are my distance observations from point 104 to 103. This is the ground distance and the standard error assigned to it, which is basically the weight. These were calculated based on my preliminary standard errors I set up in the project. The same for angles, back sight, occupied, foresight, the actual averaged angle, and the standard error assigned to it. As you can see, the standard errors aren't all the same because some angles had sets turned to them and some didn't. Next, in the unadjusted observation are my traverse closures. As you recall, I had a closure file selected that had 2 closures in it. This is the first one. I had an total angular error of 34 seconds, 2 seconds per angle point. Total distance traversed almost 5,000 feet with a closure of 107,000. My vertical error was 0.04. The next traverse was a loop traverse. Total angular error is 11 seconds, less than a second per angle point. The closure 1 in 36,000, and my vertical closure was 100th. The next piece of data shows me my actual calculated grid distances. These are the ground distances reduced down to state plane. The calculated grid factor, the elevation factor, and of course the combined factor. This is calculated for each line segment. And the last is the grid horizontal angles. Again, grid angles are very close to ground angles, so there's very little, as you can see, it's less than 1/10 of a second correction to these angles. So it's very little correction applied to angles to get them to grid. The next tab shows our adjusted observations. These are the adjusted distances, from point to point distance. The residual is nothing more than the correction applied to that distance. The standard residual, which is the residual divided by the unadjusted standard error assigned to the point. The standard residuals should be close to 1 or less. If they get above 2, we'll put an asterisk next to them so they are obvious to you and they pop out at you. You can check them out. And then the standard deviation calculated for that distance. As you can see, none of my residuals are even more than 1/100th of a foot, so this looks like a pretty good traverse. The adjusted angles, the angle, the residual in seconds, which is the actual correction applied to that angle, the standard residual, and the standard deviation. The very definition of least squares is the sum of the residuals. The sum of the square of the residuals is a minimum. By definition, least squares adjustment will make the least amount of adjustment to your measurements to get a solution. It's very obvious that the least amount of adjustment is the best adjustment. At the very bottom of the adjusted observation report, you'll see some statistics. This particular solution converged in 3 iterations. It has 22 degrees of freedom, which means it has 22 more pieces of information than it needed to actually calculate coordinates for every point. It has a reference variance of 0.5. The reference variance is a single number that gives you an overall feel for all the adjustments and how well they matched what you thought they should be. So, for example, when we set up our initial standard errors, we in essence told the program that we thought we could measure to the 1/100th of a foot plus 5 parts per million, and we thought we could measure 3 seconds per angle with a pointing error of 3 seconds. This number here shows how well we did with those expectations. If it was 1, it would mean we matched the expectations exactly. Less than 1, we did better than we thought. More than 1, maybe we're a little bit too optimistic on our standard errors. The standard error unit weight is basically the reference variance squared. This passed the chi-square test at a 95% confidence level. A lot of people think that this chi-square test is a litmus test whether they have a good traverse or a bad traverse, but that is not what it means. It is a statistical value. I can change this very easily by changing my standard errors. My standard errors to something higher, say 20 seconds, and 20. Hit OK. Process. adjusted observations. Okay, as you can see, now I failed the chi-square test. I failed it on the low end, which means that my actual adjustments were better than the actual measurements were better than I thought they would be based on my initial standard errors. You can fail the chi-square test on the low end or the high end. If you failed on the high end, you were being very optimistic with your initial standard error settings. If you fail it on the low end, you were not being very optimistic with them. So I'm going to go back up and put these back to where they were. Hit OK and process. As you can see, it's not too hard to change something and reprocess the data. So that finishes the adjusted observation tab. We're going to go to the adjusted coordinates. Here are your adjusted grid coordinates, state plane coordinates, north, east, the standard errors for each, and some very useful information, your adjusted geographic coordinates. For each point we calculate the latitude, the longitude, the convergency angle, the scale factor, the elevation factor, and the combined scale factor. At the bottom of this report are your adjusted coordinate error ellipses, your semi-major axis and semi-minor axis. You can also graphically view the error ellipses if you want to pull up your graphic file. Since I've processed them, you'll see the error ellipses have automatically popped up. Under the settings, you can select the size you wish to see your error ellipses. As the scroll bar, you can see they get larger or smaller. This gives you a nice graphic representation of your errors, the size of the ellipse and the shape of the ellipse. Also, while we're in this little dialog, you can see that you can set up your symbols for control points. We have control points, fixed control points, and float control points. Under your traverse side shots, we have traverse lines, side shot lines, and azimuths. We also have the traverse point, the symbol, and the point number, the text size. So this basically gives you a way to configure your graphics so you can see it the way you wish to. Now I'm going to go back to the report file. The next tab, since we included an ALTA report, gives me a tab that shows the ALTA certifications. As you recall, we had an ALTA file, and inside that file we had two boxes. One of them we wish to show the direct connection between these 4 points. It shows the distance, shows the actual semi-major axis, and then it shows the allowable semi-major axis. This is based on the ALTA standards of 700s plus 50 parts per million. So this was allowable 1600s, this was allowable 2/10, and the actual value was less than that. So we did pass on these 2 points. We show the ratio of the actual to the allowable. So anything under 1 passes, anything over 1 fails. The second box, we wanted to see all possible connections, and we selected all points between 100 and 200, and all points that had the description of TRAV. This will only show points that failed. We wanted to see the worst 20, but only 5 points failed the ALTA standards. So you can see the ratio. These are all points that are slightly over 1. The last tab is your elevation report. This is a 2D 1D model processing, so we process the elevation separately from the horizontal data. It shows our control points and the elevations. Shows the actual points and the difference in elevation between the points and the standard error assigned to those values. And it shows the adjusted elevation, the standard deviation. Here it shows the actual correction or residuals to each elevation difference. And as you can see, none of these points were adjusted more than 1/100th of a foot. And then the side shots are done at the end. That's basically the network least squares report. It gives you a lot of information about your traverse, and it gives you a lot of flexibility as far as determining whether your traverse is good or needs some extra work. We also have a couple of blunder detection tools that I think I'll go into and speak briefly about. I'm going to go into my raw data file and I'm going to put an error into it. I'm going to call this point 160. We already have a point 160 somewhere else in the file. This is a common error. This is where you call a point the wrong point number, or you reuse a point number that you have already used, but it is a different point. So I'm going to go ahead and put some error into this raw data file, and I'm going to process it. As you can see, it says the solution did not converge. So we have a pretty drastic error. If it's not going to converge, that's usually 90% of the time it's a problem with point numbering. So I'm going to go ahead and go to my blunder detection tools, and I'm going to select preprocess the raw data file. Now this particular, we have 3 blunder detection tools. The first one is the only one you can use if the project does not converge. It's very good about finding the type of blunder that I just put into the file. I'm going to hit apply. I'm going to exit. I'm going to look at my error report. Okay, right after the field closures we have K-matrix analysis, and it basically shows the measured distance, the initial computed distance, and the difference. So I look for something that looks drastic. This is 400ths, this is 1/10, this is 1,356 feet. Now that's pretty drastic, so I'm going to say there's either a problem with point 130 or point 160. So I can go into my raw data editor, I can find, say I'm going to look for a point number, point 160, and hit OK. Okay, it found a 160. Search again. Okay. Ooh, it found another 160. So it found the first one again. So obviously these are not the same point, but we called them both 160. I'm going to change this to 150. Hit OK. Save yes. And process. And now it processes. I will briefly discuss the other 2 blunder detection options. We have float one observation. What this particular blunder detection function does is it will allow one observation to float at a time. Let's say you have 20 angles and 20 distances. It will let one angle float and the rest of them will be assigned a standard error. It will do that for each angle and each distance, so that means it's going to process that file 40 times. If a particular angle or distance is a blunder, then all the air will go into that particular angle, and everything else will look just great. So it's very good at finding an individual angle or distance blunder. The third option is reweight based on residuals. And as I read here, it says this method can find multiple blunders, but the method works best if there is a lot of redundancy in the data set. This method will not produce meaningful results if the project is not converging. Basically, this is a function that will find blunders, but of course it does a better job if you have a certain amount of redundancy, which means like cross traverses or control points within your traverses, or locating points from multiple positions. And those are some of the tools we have. We also have some basic tools for inversing, checking relative error ellipses. We have the alter reports, but you can in real time say I want to see from 100 to 103. Oops, 100 doesn't exist. 101 to 103. Okay, 102 to 103, and it shows my relative error ellipse is 0.04, and it gives you your semi-major, semi-minor, and your error azimuth of your ellipse. We have tools for converting GPS vector files to our standard ASCII file, for converting certain types of level files. We support TopCon and Leica digital level files formats to create a level format that we can process. Of course, we can edit raw data files. You can call the data collection transfer program, which will allow you to bring the data from the data collector into your desktop software. And that's about it. I think we've hit about an hour. I hope I explained SurvNET to your satisfaction. If you have any questions, feel free to email me directly at dgoodman@carlsonsw.com. I'll be happy to answer any questions you have about SurvNET. Thank you very much.